Hello everyone, and welcome back to the channel. In the world of heat treatment, carbon is the superstar. It's the key ingredient that defines the hardness and strength of steel. But did you know that during heating, two completely opposite reactions can happen right on the steel surface? One of these reactions adds carbon while the other takes it away. These processes are called carburization and decarburization. Getting them mixed up can lead to major problems, but understanding them is your key to mastering heat treatment. In this video, we're going to break down exactly what they are, how they happen, and why they matter so much. We'll do it all in just 10 minutes. So, let's get started. First, let's cover the basic concepts. Imagine you have a piece of steel. Carburization is the process of adding carbon atoms to its surface, making it carbon-rich. Think of it like soaking a sponge in water. The steel's surface absorbs carbon. On the flip side, decarburization is the process of removing carbon from the steel's surface, leaving it with less carbon than the core. It's like the steel is losing its carbon to the surrounding environment. Both of these phenomena occur at high temperatures during heat treatment, and their direction, whether carbon goes in or out, depends entirely on the atmosphere inside the furnace. One process strengthens the surface, the other weakens it. This fundamental difference is what makes controlling them so critical. So why do these reactions happen? It all comes down to chemistry and atmosphere. Carburization occurs when steel is heated in an environment that is rich in carbon. Common sources are gases like carbon monoxide or methane, or even solid carbonaceous materials. At high temperatures, these carbon-rich sources break down, and the free carbon atoms are eager to find a new home. They diffuse directly into the iron lattice of the steel's surface, increasing its carbon concentration. Decarburization is the exact opposite. It happens when steel is heated in a carbon-deficient or oxidizing atmosphere, like plain air, which contains oxygen, or atmospheres with carbon dioxide and water vapor. At high temperatures, the oxygen in the atmosphere reacts with the carbon at the steel's surface. This reaction forms carbon monoxide or carbon dioxide gas, which then escapes, effectively stealing carbon away from the steel. So, one process is driven by a carbon surplus, and the other is driven by a carbon deficit, or an oxidizing environment that actively pulls carbon out. Let's dive into the details of each process. Carburization is a deliberate surface hardening treatment. It's typically performed at temperatures between 850 and 950 degrees Celsius. The goal is to create a very hard, wear-resistant outer layer, or case on a component, while keeping the inner core tough and ductile. This is why it's often called case hardening. You see this process used for parts that need to withstand a lot of friction and impact, like gears, shafts, camshafts, and bearings. It gives you the best of both worlds, a hard surface and a tough core. Decarburization, however, is almost always an unwanted side effect. It can happen unintentionally during forging or any heat treatment process, where the furnace atmosphere is improperly controlled. When decarburization occurs, it creates a soft surface layer on the steel. This soft layer has poor wear resistance and, more dangerously, significantly reduced fatigue strength. Components with a decarburized surface are much more likely to fail under repeated stress, which is a major concern for safety-critical parts. Now, let's look at how these two processes directly impact the mechanical properties of steel. It's a tale of two extremes. With carburization, as we add carbon to the surface hardness dramatically increases. Consequently, it's where resistance improves significantly. This also boosts the fatigue strength, as cracks are less likely to initiate on a very hard surface. The core, however, remains unaffected and retains its original toughness. With decarburization, the effects are entirely negative. By removing carbon, the surface hardness decreases, making the steel soft and easy to scratch or deform. This leads to a huge reduction in wear resistance. Even more critical is the drop in fatigue strength. The soft surface becomes the weak link, where fatigue cracks can easily start and grow, leading to premature failure. The core toughness isn't really affected, but having a soft skin on a strong part completely undermines its performance. So, if decarburization is so bad, how do we detect it and prevent it? The most reliable way to detect it is through metallurgical testing. A small sample is cut from the part, polished, and etched. When viewed under a microscope, a decarburized layer will appear different from the core material, usually showing a change in the microstructure. Another common method is a hardness profile test. This involves taking micro-hardness readings from the surface inward. A gradual drop in hardness from the core to the surface is a clear sign of decarburization. Prevention is all about controlling the furnace atmosphere. The most effective method is to use a controlled atmosphere furnace that maintains a specific carbon potential, ensuring the atmosphere is in equilibrium with the steel. Other methods include using protective coatings or wrapping the parts in stainless steel foil before heat treatment. For the highest precision, vacuum furnaces are used, as there is no atmosphere to react with the steel in the first place. Let's talk about where you see these processes in the real world. Carburization is a cornerstone of manufacturing for high-performance components. Think about the automotive industry. Gears in your car's transmission are carburized. To handle the constant meshing and friction, ball bearings, industrial dies, and cutting tools are also commonly carburized to ensure they have a long service life under demanding conditions. On the other hand, managing and preventing decarburization is critical for almost all high-strength steel applications. For example, in tool steels used for cutting and forming, a decarburized layer would mean the cutting edge is dull and wears out instantly. For components like springs or high-strength structural bolts, even a very thin decarburized layer can be a starting point for catastrophic failure under load. In these applications, controlling the furnace atmosphere isn't just a matter of quality, it's a matter of safety and reliability. Alright, let's quickly recap what we've learned. Carburization is the process of adding carbon to the surface of steel to make it harder and more wear-resistant. It's a beneficial, intentional treatment. Decarburization is the unwanted removal of carbon from the surface, which makes it soft and weak, especially against fatigue. Both of these processes are governed by three key factors: temperature, time, and most importantly, the composition of the furnace atmosphere. If there's one thing to take away from this video, it's this: controlling the furnace atmosphere is the absolute key to achieving high-quality, reliable heat treatment. Mastering this means you can dictate whether carbon goes in or comes out, ensuring your steel parts meet their design specifications every single time. Thank you so much for watching. Hope this video cleared up the difference between carburization and decarburization for you. If you found this helpful, please hit that like button and consider subscribing to the channel for more deep dives into the world of heat treatment. Let me know in the comments if you have any questions or what topic you'd like to see next. Till then, stay curious.